So the DFT and the Fourier analysis in general are not the only type of frequency-based analysis that you can use when looking at waveforms. In fact, there are many different types. We're going to explore one today called the discrete cosine transform. And to motivate this, first consider that we have some sequence x of n that looks like this. 1, 2, 3, 4, 5, 6. Go ahead and make it 8 samples long. There we are. And we can take the compute the discrete cosine the discrete Fourier transform of this, and we know that when we do, there's an implied periodicity as part of the discrete Fourier transform. And this implied periodicity is going to have a large effect on the coefficients in this particular case, because we're essentially trying to come up with a waveform, a set of cosine waveforms or sine waveforms that can be used to describe this replicated sequence. Well, you could imagine if all we had were these blue samples, that actually looks very much like a part of the cycle of a single cosine. Not perfectly, but pretty close. And we would expect that cosine of that particular frequency, basis function of that particular frequency, to have a large value and the rest to be pretty small. But whatever we do, it also has to account for this big jump between samples. And so now, in order to get that, there will be a lot of high frequencies that come in. So what started out looking like a relatively low frequency, now suddenly our DFT is polluted with a lot of high frequencies because of this periodic extension that goes with the DFT. So we're going to come up with a new method of getting rid of this particular problem, and we'll see that it has far-reaching effects. So the way we're going to fix this, or try to fix this, is to change our periodic extension. And we'll do that by manually extending our waveform. Let's do this now in a flipped manner, like this. So we started with the black samples, and we create these red samples to go along with it. Then we can take the DFT of our new sequence, and it will do a periodic extension, but that periodic extension will not have the discontinuities that we saw before. So this periodic extension is going to actually come up with something that looks pretty well behaved in terms of its frequency content. This isn't a perfect sine wave. I didn't mean it to be, but it actually looks pretty close to one, doesn't it? So that continues on that way, and we do the same on this other side. So we're going to call this new sequence here x tilde of n, and x tilde of n will equal x of n for 0 less than or equal to n less than capital N. See, I haven't given myself a whole lot of room, and this looks a little bit cramped. Let's move it down here and spread it out just a bit. Okay. So look at this for a second and convince yourself that this works. If n is equal to 0 to n minus 1, just x tilde is going to be equal to x of n. So we haven't done anything fancy. Once we're equal to n, then 2n minus 1 minus n is going to be n minus 1, which is that one. And now we're working backwards all the way up to when n is equal to 2n minus 1, in which case this is going to be here corresponding to x of 0. So that's 2n minus 1. And so now we have a sequence that's 2n long, and we've replicated it this way. This is a good time to point out that there are other ways of doing this replication. And one of them is to not replicate the last sample. So in that case, if you had something like this, instead of replicating it that way, we would do it this way. And they lead to different definitions of the DCT. There's the DCT1, which is this method I just showed you, the DCT2, which is the one I'm showing you right now, and also a DCT3 and a DCT4. So we're just going to spend our time working on this particular one right now. So now that we've developed this new sequence, let's see what happens when we take the DFT of that sequence. Okay, so things look just the same. We have a length 2n DFT, and so we define it like that. And let's go ahead and add in now what we know about our x tilde of n. So I've divided this out. It looks like the first term is a regular DFT, except that we have the 2n in the denominator there up in the exponent. And the second term has this crazy 2n minus 1 minus n in there. So the first thing let's do is do a change of variable and see if that will help. So in this case, let's just say m is equal to 2n minus 1 minus n. It's good. And so now, accordingly, n is going to be equal to 2n minus 1 minus m. And we can plug that in wherever we see n, and away we go. So this second term, then, when n is equal to capital N, m will be n minus 1. And when little n is equal to 2n minus 1, m will be 0. Since we're just summing up points, let's put this in the correct order, 0 to n minus 1. So we're summing up all those points, and that should be an m. Now we have xm. Then this is going to get crazy, of course. 2 pi k, and now we're going to have 2n minus 1 minus m all over 2n. So we have a little bit more work to do to simplify that. This 2 pi k times 2n, 2 capital N divided by 2n, that all comes out to be an integer, and an integer multiple of pi. So we can go ahead and cancel that. That doesn't matter. The other terms do. So now we have 2 pi k minus times this negative n m minus 1 term up there. Okay, let's carry this on to the next page because we have some more simplification to do. Okay, so I've copied this now from the other page, and we need to figure out what to do with it. It turns out that things aren't going to work out quite as directly as we hoped, but that's okay because it'll all eventually get there in the end. We just have to use a few little tricks. So the first thing we notice is that I took out the 2n, crossed out here in green on the lower part there. And next we can come in and we can cancel out these 2's out there. Finally, we can combine these two equations into a single sum and go back to our index n. And so we get e to the negative j pi kn over n plus e to the positive j pi k n over n, and then we have this extra term out here, e to the j pi k over n. So it looks like we've got a cosine-like operation going on in here, but we have this extra term. So we can factor that out, and we get 2. Now I'll do it in 2 steps here. So we have e, j. We're going to factor this out by factoring out a k over 2 factor. So that, to cancel that, we have a negative k over 2 in the left term, and then the positive term on the right there becomes just a k over 2. So this is going to be e to the minus j pi k n plus 1/2. That gives us a k over 2 over n plus e to the negative j pi k n plus 1/2 all over n. Oh, this is looking good. Turns out it is looking good, but we'll see it's not exactly what we want. What we really want is a real transform, and this pi k, I'll put the 2 down below, over 2n cosine pi over n plus 1/2 k. This term right here is kind of mucking up the works. It's not going to give us a real transform, which was our real goal. Well, where does this come from? Let's go back and take a look. It comes from this, the way we did our replication. So if you look at this right here, you can see that it's not really an even function. If we want just pure cosines with no other terms, we would want this to be a perfectly even function. And so in order to do that, we invoke kind of a crazy trick. We redefine the axis. And what we're going to do is define that to be 0. So we move it over. So now our new 0 is right in between there, and we get this axis. So where does that come from? What does that do? Well, remember, a shift in time has an effect in frequency, and we know that. So let's factor this out. Just write this down completely. We now have this Fourier transform with a shift in time. Well, how much is that shift in time? The shift in time is by k over 2. And now I'm going to put all the factors out here so it's kind of clear and it matches what we've seen in our tables. Because remember, we were taking a 2n length DFT. And so we've got this factor out front. We also have our 2. And then we have the sum from 0 to n minus 1 of xn cosine pi n plus 1/2 k. This corresponds to a shift by 1/2. So we just assume that we can do that. There are several reasons why, and we could go into all of them, but here's just a summary. The first is we could just simply define a new axis where all the samples are on the 1/2. The minus 1/2, plus 1/2, plus 1.5, plus 2.5. And that's our new index. And we just define it that way. And then everything works out. And the DCT ends up with a negative phase term, which cancels this one out front. And so that one would go away. Okay, so that's one way to do it. There's another way to do it that's a little bit more rigorous and also a little bit harder to understand, which essentially shifts the whole sequence to the right, and then actually at first it upsamples. It puts zeros between every sample, shifts it to the right, computes the Fourier transform of now length 4n, and then it downsamples in time, or downsamples in frequency by getting rid of the upper frequencies, and you come up with the same result. It's another way of developing it. And the final way of developing it is to say, well, let's just leave it where it is. We will shift all the basis functions to the left by a half sample. As long as we have all these basis functions, if we shift them left by half sample for our defined kind of a new DFT, these functions still form a basis, and so everything's okay. And that's kind of the third way of getting at it. But the long and the short of it is, we do a little bit of magic, and we can justify it in a variety of ways. And we get rid of that little phase term out front. So the actual DCT2 is defined as the sum times x of n, and now instead of the complex exponential we have cosine of pi over n n plus 1/2 times k. Now, as I mentioned, there are different definitions of the DCT. This is the most common one, and when someone says the DCT, this is typically what they mean. There's also one, or the inverse in DCT, and you don't normally have the subscript DCT, but I'm doing that just to differentiate it from the DFT in this particular case while I introduce this. Is very similar. It once again uses a cosine function, and here though we have our normalization factor as we did with the DFT over on one side. Other versions of the DCT2 actually define it as 1 over the square root of n forward and backward. But this one does it this way, and we have, oops, once again, pi over n times n plus 1/2 times k. Normally we would have a conjugate when we do our inverse operations, but the conjugate kind of disappears here with the fact that we have even or real functions. So this is our DCT. So just as a kind of a comparison with the DFT, the DCT frequencies are characterized by the fact that they have a pi up front here instead of 2 pi, which means that the frequencies are half as much. And so when we go to k all the way up to capital N with the DFT, we have now gone around and hit the negative frequencies. But the DCT doesn't do that. The DCT only has the positive frequencies. And they're twice, they're spaced twice as closely, or twice as many. So, let's see, I'll have a little bit of room here. I'll put down some of the DCT basis functions and compare those with the cosine, or the DFT. Okay, so here we have the DFT basis functions, at least the first 6 of them, for n is equal to, capital N is equal to 16. And you see we have the DC1 with k equals 0, and then just to the right of it we have the first one, which shows a single period, the cosine, and the imaginary part, the sine, is in red. Then on the right you see the DCT basis functions. You have a DC part for k equals 0, and then k equals 1, you can see we have half a period of a cosine. And then at k equals 2, we have the full period. So k equals 1 for the DFT and k equals 2 for the DCT have the same real part, but the DCT lacks the imaginary part. For the DFT, when k equals 2, we now have 2 periods of that waveform. But for the next one in the DCT is 1.5 periods of a waveform. And we don't get 2 periods until k equals 4. So we have twice as many frequencies in the DCT. They're closer together, and we lack the imaginary part. So, and the other thing that I mentioned before is that as we get to higher and higher frequencies, the DCT finally gets up to, which is essentially the frequency that's essentially the frequency pi, whereas the DFT gets up to a frequency of 2 pi, which is then translated to negative frequencies. So that's our DCT. We'll see that again when we talk about JPEG coming up.